Let me tell you what happens if you fall into a black hole. Well, the first thing I have to tell you is that from your perspective, falling into a black hole takes a perfectly ordinary amount of time. You fall, you cross the event horizon, you keep falling, and eventually you reach the singularity at the center. The whole trip might take a few seconds for a small black hole, maybe a few hours for one of those supermassive black holes at the centers of galaxies. But from the perspective of someone watching you from far away, something very strange happens. They never quite see you reach the event horizon. You get slower and slower and slower. Your light gets redder and redder and redder until you appear to freeze at the edge, frozen there forever. And here is the thing. Both perspectives are correct. That is relativity. Now, this is one of the most beautiful and strange predictions Einstein ever made. And unlike some things in physics that are just theoretical ideas, this happens. We have seen black holes. We have photographed them. In 2019, scientists took a picture of the event horizon of a black hole at the center of a galaxy called Messier 87, 55 million light-years away. And there it was, exactly as Einstein predicted, a dark circle surrounded by glowing light, the point of no return made visible. So let me tell you what it would actually be like to fall into one of these things. You see, we need to pick our black hole carefully. Not all black holes are the same. There are stellar mass black holes, maybe 10 times the mass of the Sun, formed when massive stars collapse. And there are supermassive black holes, millions or billions of times the mass of the Sun, sitting at the centers of galaxies. The size matters enormously for what happens to you. For this story, let us say you are falling into a stellar mass black hole, about 10 solar masses. The event horizon, the point of no return, would be about 30 kilometers across, and you are falling in feet first. Now, here is what starts to happen. The gravity of a black hole is not uniform. Your feet are closer to the center than your head, so your feet feel stronger gravity than your head. This difference, this gradient in the gravitational field, creates what we call tidal forces. And near a black hole, these tidal forces become extreme. Your feet are being pulled harder than your head, much harder. The technical term for what happens to you is spaghettification. You get stretched like a piece of spaghetti, your body elongates. At the same time, you get compressed from the sides, squeezed. The tidal forces do not just pull you apart lengthwise, they squeeze you narrower. Now, when does this become noticeable? Well, that depends on the size of the black hole. For a stellar mass black hole, the tidal forces become extreme well before you reach the event horizon. Calculations show that for a 10 solar mass black hole, the tidal forces would tear your body apart when you are still hundreds or thousands of kilometers away from the horizon. You would not survive to cross it. Your atoms would be ripped apart. You would be reduced to a stream of particles falling inward. But here is something interesting. For a supermassive black hole, the event horizon is much, much larger, millions of kilometers across for the really big ones, and the tidal forces at the horizon are much weaker. Why? Because the gradient depends on how rapidly gravity changes with distance. For a supermassive black hole, the curvature of space is gentler near the horizon. You could cross the event horizon of a supermassive black hole and feel nothing special at all. No pain, no drama. You would not even know you had crossed it, not immediately. So let us switch scenarios. Let us say you are falling into a supermassive black hole, 4 million solar masses, like Sagittarius A star at the center of our Milky Way galaxy. You are falling in and you are holding a watch. You look at your watch, it ticks normally. 1 second per second. You feel fine. You look around. You can still see the stars, though they look distorted, bent by the intense curvature of space. And then you cross the event horizon. Nothing happens. No barrier, no wall, no sensation. The event horizon is not a physical surface. It is just a mathematical boundary in spacetime, the point where the escape velocity equals the speed of light. Once you cross it, all your possible future paths point inward. You cannot turn around. You cannot escape. But locally, at the moment of crossing, nothing feels different. You see, this is one of the strange things about general relativity. Whether something is falling or not depends on your perspective. If you are in free fall, you feel weightless, you feel nothing. Gravity is not a force pulling you. Gravity is the curvature of space-time, and you are following the straightest possible path through that curved space-time. A geodesic. From your perspective, you are just floating there, weightless, while the universe does strange things around you. But here is where it gets really interesting. You look back at the universe you left behind. What do you see? Well, you see something very strange. Time dilation. Because of the extreme curvature of space-time near the black hole, time passes differently for you than for someone far away. From your perspective, falling toward the singularity, you look back and you see the outside universe sped up. You see stars evolving rapidly. If you looked at Earth, you would see time accelerating, days flickering by like seconds. For a supermassive black hole, this effect is not too extreme near the horizon. But as you fall deeper toward the singularity, the time dilation increases. The universe outside ages faster and faster from your perspective. Now, let us think about what someone outside sees. Your friend is watching you fall in from a safe distance, far from the black hole. What does your friend see? Well, as you get closer to the event horizon, your friend sees you slow down. Your watch, which you are holding up so your friend can see it, appears to tick more and slowly. One tick, long pause, another tick, longer pause. You are moving slower and slower. And your light, the photons bouncing off you and traveling out to your friend, those photons are climbing out of a deeper and deeper gravitational well. They lose energy doing that. They get redshifted. You appear to turn red, then dim, then disappear. Your friend never actually sees you cross the horizon. From their perspective, you asymptotically approach the horizon, getting slower and dimmer, frozen at the edge forever. Both of you are correct. This is not a contradiction. This is how space-time works. You see, the event horizon is a null surface. It is made of outgoing light rays that are not going anywhere. Light emitted exactly at the horizon stays at the horizon. It neither escapes nor falls in. It is stuck there. So as you approach the horizon, the light you emit takes longer and longer to escape. It gets stretched out. By the time you cross, the light you emit cannot escape at all. Your friend stops receiving information about you. From their perspective, you fade away at the edge. From your perspective, you sail right through. And now you are inside. Inside the event horizon, the nature of space-time changes in a very strange way. Outside the horizon, the radial direction, toward or away from the black hole, that is a spatial direction. You can go toward the black hole or away from it, and the time direction is time. But inside the horizon, these switch roles. The radial direction becomes time-like. The direction toward the singularity is not a place, it is your future. You cannot avoid moving toward the singularity any more than you can avoid moving forward in time. It is inevitable. Not because something is pulling you, because that is the direction time points. The singularity is not a place in space that you could, in principle, avoid. It is a moment in your future that you cannot escape. Think about that. Now you keep falling, and the tidal forces start to increase. Even for a supermassive black hole, the tidal forces grow as you approach the center. Eventually, they become extreme. Your body stretches, then your molecules stretch, then your atoms. The singularity is not just a point of infinite density. It is a place where general relativity breaks down completely. The equations give infinity, infinite curvature, infinite density. This tells us something important. It tells us that general relativity is not the final answer. At the singularity, we need a theory of quantum gravity. And we do not have one. Not yet. Nobody knows what actually happens at the singularity. The equations cannot tell us. But wait, there is more. So far, I have been talking about a non-rotating black hole. A Schwarzschild black hole named after Karl Schwarzschild, who found the first exact solution to Einstein's equations in 1915. Just months after Einstein published general relativity. Schwarzschild was serving in the German army during World War I, and he did this work in the trenches. Incredible. But real black holes rotate. They have angular momentum because the stars or matter that collapsed to form them were rotating. A rotating black hole is described by a different solution found by Roy Kerr in 1963. And rotating black holes have very different internal structures. A Kerr black hole has two event horizons, an outer horizon and an inner horizon called the Cauchy horizon. And inside the inner horizon, there is a ring singularity, not a point singularity, a ring of infinite density and curvature. Now, here is something that sounds like science fiction but comes straight from the mathematics. For a rotating black hole, it is possible, in principle, to avoid hitting the singularity. The ring singularity has a hole in the middle. You could, according to the equations, pass through the ring and emerge into a different region of space-time, maybe a different universe, maybe another part of our universe. But there is a problem. The Cauchy horizon is unstable, infinitely unstable. Any small perturbation, any tiny bit of energy or matter that falls into the black hole gets blue shifted to infinite energy at the Cauchy horizon. The energy piles up there and the horizon becomes a firewall of infinite energy density. You would be incinerated. This is called the mass inflation instability. It suggests that even in a rotating black hole, you probably cannot survive to see what is inside the ring singularity. The instability destroys you first. So the romantic notion of black holes as portals to other universes, while mathematically possible in idealized solutions, probably does not work in reality. The instabilities intervene. Now, let me tell you about something else. Something that happens to black holes over very, very long times. In 1974, Stephen Hawking discovered that black holes are not entirely black, they emit radiation. Hawking radiation. This was a shocking discovery. Black holes, by definition, are objects from which nothing can escape. But Hawking showed that when you combine quantum mechanics with general relativity, black holes radiate. They emit particles. And by doing so, they lose mass. Very, very slowly. Here is how it works. In quantum field theory, empty space is not really empty. The vacuum is full of virtual particle pairs appearing and disappearing constantly. An electron and a positron, a photon and another photon. These pairs pop into existence, exist for a tiny fraction of a second, and then annihilate each other. They do this because of the uncertainty principle. Energy can be borrowed for a short time as long as it is paid back quickly. Now, if one of these virtual pairs appears right at the event horizon of a black hole, something strange can happen. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real. It carries energy away from the black hole. The black hole loses that energy, which means it loses mass, because mass and energy are the same thing. The black hole evaporates. Slowly. How slowly? Well, for a stellar mass black hole, the evaporation time is enormous. A 10 solar mass black hole would take about 10 to the 67 years to evaporate. That is 10 million trillion 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 years. The universe is only about 14 billion years old, so stellar mass black holes effectively live forever, for all practical purposes. But smaller black holes evaporate faster. If a black hole has the mass of a mountain, it would evaporate in about the age of the universe, and a black hole with the mass of a car would evaporate in a tiny fraction of a second, exploding in a burst of gamma rays. People have looked for these primordial black holes, small black holes that might have formed in the early universe. They have not found any yet. Now, the evaporation of black holes creates a famous problem, the information paradox. Suppose you throw a book into a black hole. A book contains information. The arrangement of letters on the pages. That information seems to disappear into the black hole. And then the black hole evaporates. Hawking radiation, as originally calculated, is perfectly thermal. It has no information content. It is just random heat radiation. So the information in the book seems to be destroyed, gone forever. But that violates a fundamental principle of quantum mechanics. Quantum mechanics says that information cannot be destroyed. The state of a quantum system evolves in a way that preserves information, always. If you know the state of a system now, and you know the laws of physics, you can calculate what the state was in the past or will be in the future. Information is conserved. So which is it? Does the information escape somehow in the Hawking radiation, encoded in subtle correlations we have not understood yet? Or does quantum mechanics fail for black holes? This is the black hole information paradox. Physicists have been arguing about this for nearly 50 years. Most physicists now think that information is not destroyed. Hawking himself eventually changed his mind about this. In 2004, he conceded a famous bet on the subject. The current leading idea is that information does escape, but in a very scrambled, encoded form in the Hawking radiation. The radiation is not perfectly thermal. It has subtle quantum correlations that encode the information that fell in. But how exactly this works, nobody knows. It probably requires a theory of quantum gravity to fully understand. String theory, loop quantum gravity, other approaches, they all try to address this, but we do not have a complete answer yet. Now, let us talk about what we have actually observed, what we know for sure. Black holes are not just theoretical. We have overwhelming evidence for their existence. We have observed stars orbiting around invisible massive objects at the centers of galaxies. At the center of our Milky Way galaxy, there is an object called Sagittarius A star. Stars orbit around it. By tracking their orbits for years, astronomers have measured the mass of Sagittarius A star, 4 million times the mass of the Sun, packed into a region smaller than the orbit of Mercury. The only object that could be that massive and that compact is a black hole. Andrea Ghez and Reinhard Genzel won the Nobel Prize in 2020 for this work. And then there is the photograph. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, not Sagittarius A star, but the supermassive black hole at the center of the galaxy, Messier 87. This black hole is 6.5 billion solar masses. The image shows a dark circle surrounded by a bright ring of glowing gas. The dark circle is the shadow of the event horizon. Light emitted by gas just outside the horizon, some of it falls in and some of it escapes to reach us. The result is that glowing ring. And the size of the shadow matches exactly what general relativity predicts. It is Einstein's theory made visible. We have also detected gravitational waves from black holes. In 2015, the LIGO detectors observed gravitational waves from two black holes, each about 30 solar masses, spiraling into each other and merging. The waves matched the predictions of general relativity with extraordinary precision. Rainer Weiss, Barry Barish, and Kip Thorne won the Nobel Prize in 2017 for that discovery. Since then, LIGO and other detectors have observed dozens of black hole mergers. We are now doing astronomy with gravitational waves. We are listening to the universe ripple. So black holes are real. They are out there, thousands of them in our galaxy alone, millions in the universe. Now, let me tell you what bothers me about all of this. What bothers a lot of physicists. We have this beautiful theory, general relativity, that describes black holes. And it works. It predicts things we can observe. Event horizons, gravitational waves, the bending of light. But at the singularity, the theory breaks down. It gives nonsense, infinity. And we have another beautiful theory, quantum mechanics, that describes particles and fields. And it works. It predicts things we can observe, Hawking radiation, the structure of atoms. But when we try to combine quantum mechanics with general relativity, we get contradictions. The information paradox, singularities. We do not know how to make them work together, not completely. This tells us something important. It tells us that we are missing something. Some deeper theory, some framework that contains both general relativity and quantum mechanics as special cases. Quantum gravity. String theory is one attempt. Loop quantum gravity is another. There are others, but none of them are complete. None of them have made predictions we can test. Not yet. And that, I think, is one of the most exciting things about black holes. They are not just amazing objects in their own right. They are laboratories for the most extreme physics imaginable. Places where our best theories fail. Where nature is trying to tell us something we have not figured out yet. The singularity is nature saying, your equations do not work here. you need something better. So what actually happens at a singularity? Nobody knows. Does space and time break down into some quantum foam of fluctuating geometry? Does the singularity not exist at all, replaced by some quantum structure? Do black holes connect to other universes through wormholes that our current theories cannot describe? We do not know. Nobody knows. And that is not a failure. That is the frontier. Think about that. We live in a universe where black holes exist, objects so extreme that they break our best theories, objects that warp space-time so severely that time and space switch roles inside them, objects that might preserve or destroy information in ways we do not yet understand, and we can observe them, photograph them, listen to them collide. And here we are, made of atoms that were forged in stars, some of which collapsed into these very black holes, trying to understand how it all works, trying to figure out the rules of the universe. That is what physics is. You find something that should not make sense according to your current understanding, and then you work to understand it. You build better theories, you make predictions, you test them, you discover that the universe is stranger and more beautiful than you imagined. Black holes are not just science, they are nature at its most extreme. They are Einstein's equations taken to their logical conclusion. They are the places where our understanding ends and the mystery begins. And that mystery is what makes physics so beautiful. We do not know everything, not even close. But we keep looking, we keep calculating, we keep building better telescopes and better theories. And slowly, piece by piece, we figure it out. And if you ever do fall into a black hole, well, from your perspective, you will reach the singularity in finite time. You will see the end of your journey. But from the perspective of the rest of the universe, you will remain frozen at the edge of the event horizon forever, a ghostly image slowly fading into the darkness. Both perspectives are true. Both are descriptions of the same reality. That is relativity. That is how space-time works. And that, I think, is beautiful.